Hello and welcome back to Calculus 3, section 12.5, chain rule. It's technically chain rules because it should be plural, because pretty much every situation will call for a different formula. In Calculus 1, there was a single formula for chain rule. And then we said if we chain more than 3 functions, we just keep nesting. But in Calculus 3, we have more issues than just multiple nesting, which is we have issue of multiple variables and multiple parameters. So we can have z to be a function of x and y, and then those x and y could be a function of t, but they could also be a function of t and s. We can have function z to be a function of x, y, and z, and then each one of these individually to be a function of parameter t or parameter s or parameter t and s, and then or rst. So each one of these situations will call for a different formula for chain rule. There is no formula for chain rule in Calculus 3. We are going to learn we're going to develop the method that will help us write the formula once we see the problem which we are supposed to differentiate. So, going back to Calc 1, right? We say that the derivative of function composition is the derivative. Oh, hold on. There we go. So the derivative of the outer function times the derivative of the inner function. And this is the only formula for derivative that you have in Calculus 1. Now you also see over here this dx. We say you are taking the derivative in respect to dx, in respect to x. And you can see that x, right, in the formula as well. Well, now we are going to have multiple input variables that are all of the same importance, or the weight category, whatever you want to call it. So they're all independent variables, and they all contribute to the derivative, right, if you're taking the chain rule. So sure, we understand there are partial derivatives, and then there are these Calc 1 full derivatives. But when you do the chain rule, a lot of these different situations is going to pop up. So let's first understand that we can say z is equal to the function of x and y. And then I can parametricize x as some function of t and y as a different function of t. So this is in the realm of our Calc 3 now. I have a function that is three-dimensional in nature, right, because you have x, y, and z. It has a two-dimensional input, the two-dimensional domain, one-dimensional output, so 2 plus 1 is 3, so 3D. But then each one of these x and a y is parametricized through parameter t. Now, I could parametricize those through parameter t and s, and then rst, and so on. So I can keep adding, and I can add even dimensions to the parametrization of dimensions, right? How far can we nest this? As much as application requires. But what you see over there is the simplest possible case. You have two independent variables, and each one of those independent variables is parametricized by a single variable, which is parameter, single parameter. So this is the easiest, cheapest, and most simple concept that we have for our derivative. Now, the way to figure out the formula for the derivative is to learn how to draw a tree diagram that you will follow along the branches and construct the chain rule formula looking at the tree. So every problem we do today will start with us drawing the tree first and then looking at the tree and figuring out what the formula for chain rule is. So what is the tree? Tree is simply going to take this information and create a map, a road map, or a diagram, whatever you want to call it. At the top sits Z. Z is produced by X and Y, and both X and Y are produced by these functions of T. So this is the tree diagram for this situation, and as I said, this is the simplest you can get in Calc 3. Clearly, if you remove branches of T, you just have Z, f, x, y, and we took care of that last class with partial derivatives, right? So what is the chain rule part? Well, it's this extra stuff, g of t and h of t, which puts those functions inside. If you observe this notation here, you see that it's f of g. Now, if I am to insert these puppies here and here, right, you will have f of g of t, comma, h of t. And that's what creates the chain rule. Now, let's see what is the derivative. What I'm looking for is the derivative of z in respect, so derivative of z in respect to t. So that's what I want to figure out. Observe that your job is to start at z, which is on the top, and go through the tree down all the way down to t's. All right. First order of business is to go down the red path. Red path says z is branching into x and a y, so I must use partial derivatives because there is because x and y equally give rise to z. So partial z, partial x. And now to go from x into a t is a straight through, only one variable, therefore we can use the regular derivative dx dt. You wouldn't be wrong if you put partial in there, but again, you know. Then we say plus, and then we follow the blue path towards t. I have again partial z, partial y, and then dy dt with regular d's because it's a straight through. Now, I don't know which way you're going to write this in your notes, but what you should write in your notes is, anytime you hit branching, I don't care if it branches into 2 or 3 or 15 of these, as soon as you hit branching, it's partial derivatives. If you have a single straight through, it is going to be regular d's. So, when you are, guys, you have to construct this formula from the tree every time. Every problem that we write in Calculus 3 to take the derivative by chain rule is going to have a different formula. Right? I showed you Calculus 1. One formula fits all of the problems. Calc 3, each problem has its own formula. So, you use information to create the tree. Once you have the tree, you follow branches all the way from the dependent variable, z, w, whatever it is, all the way down into the parameter variables at the very bottom. You will go each branch separately, how many branches you have, and again, every time when it branches, you use partial derivatives. Anytime it goes straight through, you will be using regular derivatives. So what we did over here is we created a formula. The rest, well, I hope you can do the rest, which is you plug the functions in and you solve the problem. So this is our formula for this situation. Now I can go and say, you know, just as an example, I can say let z be the sine of xy, and then let x be e to the t, and y be t squared minus 2. All right? Well, all I need to do to find this derivative is to take a whole bunch of these partial derivatives and regular derivatives, stuff everything up there, and simplify. So that should be all Calculus 1 work, and it should be no effort for any of you. So what is the partial z, partial t? Well, I need partial z, partial x. We will be looking into this one to get partial z, partial x. So partial z, partial x is the derivative of sine is cosine of xy, and then because I'm taking the partial derivative in respect to x, y is considered as a constant, which is what y would pop up in front, times the derivative dx dt, which is just e to the t. And then we have plus partial derivative dz dy is going to be x cosine xy, and then finally times the derivative of 2t. Are you done? No. Your question is asking you to provide the answer in terms of t. What do you have? Whole bunch of x's and y's that all have to go away. And the way to get rid of them is to use the conversion between x's and t's, so and y's and t's. So you are going to now replace every x with e to the t, every y with t squared minus 2. So now you're seeing this labor, right? The one that I say the problems are excellent for killing time and developing carpal tunnel. So that's this. So now I'm replacing for every y, t squared minus 2, cosine, x is e to the t times t squared minus 2, and now everything times e to the t. So I'm just substituting stuff now. Cosine e to the t squared minus 2 times 2t. All right, so now I can factor the e to the t, cosine e to the t. So factor out e to the t, cosine e to the t, t squared minus 2. Maybe just for the sake of argument, let's use the green one. This is all argument of cosine. Just want to make sure that we all know that. There we go. So now I pull out e to the t and cosine e to the t, t squared minus 2. What's left behind is t squared minus 2 plus 2t. And if I am to put this in order, well, I can write over here the final answer: e to the t, cosine e to the t, t squared minus 2, and then in parentheses, so all of these times. You know what, I'll put polynomial in front. Oh, you write in pen? Awesome. So t squared plus 2t minus 2, and then we'll do cosine of e to the t, t squared minus 2. I'll add these green parentheses to again emphasize that all of this is the argument of cosine. And that would be the answer. Again, you shouldn't be labeling this hard. You are just inexperienced now. And as you start working on homework and so on, you'll get much better, and this will be very smooth and quick. It does look intimidating, but it's as simple as you just chase the variables around. That's all you're doing. You're chasing which function belongs where, what plugs into what, right, once you have the formula. So your connection between x and t's and y's and t's is always given to you, and then you can plug them in here. So that's that part. Let's take a look at the next situation that we might. There's no way for me to do every single flavor that is out there, right? Say your function, say z is the function of x and y. And now your x is a function of s and t, and your y is a function of s and t. Now I have two parameters that are driving the function, which is driving the variable that is driving the function, right? What could be the two dimensions that are driving, right? So let's say this is in a domain, so these two will definitely describe a path for the particle, right? So what do we have? S and t. Well, t could be time, right? And what could be s? Sadness factor, all right? If you're sad, depressed, you're not going to move as quickly as if you're excited and happy to get somewhere. All right? It's a parameter. It's fine, right? You can think of anything, guys, as long as it impacts the situation that you are thinking about. So it brings the dimension, right? So what do? We create the tree so that we can create the formula. Let's work on the tree. We are starting at z, and as you can see, z branches into x and a y. And now you get an x and a y, and they do what? Branch into s and t, each one of them. So x branches into s and t, and y branches into s and t. Perfect. What's next? Next is to follow the paths. Now, guys, what should I be asking? Well, I should be asking for the derivative in respect to t. Now, look at my notation for the derivative changed. Right? I used dz, dt, regular d's in a previous one, and the reason for it is that the last row last time didn't have branching. Now it does. So, I mean, you can, to avoid confusion, you can always use partial derivatives, but then it's harder to follow the work. So, yeah. Guys, please observe that I have from z to t and from z to t. I have two red paths. So I'm going to take the two red paths and say partial z, partial x, because there was branching, right, at z, and then times partial x, partial t, because there is branching at x. So I have a branching and then branching again. So these are all partial derivatives. Plus, I have another red branch which takes me from z to t. So partial z, partial y, partial y, partial t. And we're done. That would be the formula for the derivative of z in respect to t. Now I want the other one. What is partial z, partial s? Well, that's going to be this blue path, which we take. Again, branching at z, therefore partial z, partial x. Branching at x, partial s. Plus, branching at z, so partial z, partial y. Plus partial y, partial s. Now, these are the formulas that we got by observing the tree. Now I want to ask you to, please look at the screen, all right? Stare at the screen and let me show you the check procedure over here. If I cancel these dx's, what do you see? What's left? Exactly, dz dt. And if you cancel dy's, what's left? Right. Dimensionally, you can only add same dimensions. So you add money to money, number of trees to number of trees, right? Those all belong to the same dimension. So if I am to add these, right, for the total partial derivative, well, I better be adding dz dt to dz dt. Now, yes, we went to a different branch, which warrants to have these guys as well, but as soon as you cancel them, you see that everything, all ducks are in a row. Nothing? Okay. Yes?
Is it possible to get a scenario where like x is a function of like g only of t, and then y is g or h of st?
Yes.
And you have to do that for.
You can get anything. You can get anything. Your job is to learn how to create the tree and follow the branches. You have to get from z to t, and you have to do it in every available branch. Yes, I can have z branch into 15 of these, and then 10 out of those 15 will have s and t, and then the rest of the remaining ones will just have t. It's okay. It's okay. Yes?
Why is the first part of the equation partial dz over dt and not
Because you mean the black?
Yeah, the black part.
Because again, I said in the back, right? When you're getting to t, you got to treat to branching, right?
Yeah.
So where on the top over here, it was a straight through. So there was no right. It was a straight through. So this is a regular derivative because.
Yeah, I thought
it's a straight
like z to t had two routes, so we learned that there are two routes that you can take.
You are still getting to dt, right?
Yeah.
So if I cancel dx, dz dt, cancel y, dz dt, right?
Yeah.
So both end the t. But now we have s and t. So we actually have two separate derivatives to worry about. There is a derivative that it's in respect to t, so the red branches should fish through to get to t, and then the blue branches, right, the blue paths should fish through to get to s's. And why it's partial on the black side over there? It's because it is, on the left side, the one in black. It's a partial derivative because you had s and t. You have two equally important, two equally weighted parameters that give rise to x. And then x and y, equally important variables that give rise to z. So because the branching was involved in the last one, we are using partial derivative there. W is equal to f of x, y, and z. W? Yeah, talk about temperature, talk about density, talk about any quality that you can think of where that could exist in whatever concept regarding a 3D object, right? So your 3D object is perfectly explained, right, by x, y, and z. Bringing in the fourth variable could be the temperature distribution, could be the density distribution, could be whatever else. So this situation is viable, right? Now, what am I going to have? Well, parameterization again. And now I'm going to say that x is g of s and t. Y is age of s and t. No, and then z is k of s. No t. It's just k of s. Because we can. It is your job as engineer to find application and recognize application that would call for such an equation. But the mathematics is abstract and arbitrary. You can do whatever the hell you want. That's the beautiful. That's why it's based for everything, right? Abstractly, you put whatever you want, and then it takes genius on the other end to recognize those mathematical patterns and actually make some, like Tesla, for instance, right? Tesla figured out that the complex numbers would give rise to alternating currents. So he was able to morph that mathematics, right, from mathematics into physics, into engineering, and give us technology we have today. All of the technology we have today is Tesla, right? Everything, including the processors, including the wireless transmission, the radio, TV, everything came from here. Electrical motor that runs everything, every factory, every every fan. What? No, interestingly enough, car is actually on DC.
Oh, it is actually.
So the battery is DC, and then you have inverters that would create alternating current for the motor, but the car battery is DC. So the car is not purely AC. And Tesla was only interested in AC because DC currents you can't transmit on long distances. DC currents are excellent for electric chairs, for instance. That and batteries for cell phones. Those are the two prime uses for DC currents. Everything else is alternating currents. So now what we are going to do with this problem is immediately create the tree. Actually, I'm going to give you guys about a minute and 7 seconds to try and draw the tree on your own. And then I'll kick in, and if you need to correct. Yes?
I just have a question. Like would the Z be a straight one or a branch one? Because it only goes to S. So is that straight? It's a straight one, right?
That's a straight, yes. There's only one. Let me see those artists. You all have pencil and then two colors for path, right? You all good.
Yeah, I'm just doing dotted line.
Dotted line and solid line. See, that's the that's good.
Smaller dots.
Smaller dots.
But it's so symmetrical.
Fix it? I would, but I'm sitting down. All right, that's your minute and 7 seconds. So let's take a look at the problem. We are starting at W, and W is going to branch into 3 variables X, Y, and Z. X will further branch into S and T. Y will branch into S and T, and Z will only have S. So what is our partial W, partial T? Well, let's draw red paths to connect W to T. There's one, and there's another. Those are the only two we have. So I have branching at W, so partial W, partial X. And then I have branching at X, so partial X, partial T. Plus partial W, partial Y, partial W, partial T. I mean partial Y, sorry, partial T. There we go. So those are red paths, and we are done with that formula. Then we are interested in partial W, partial S. Now that's going to be blue.
It's making me mad. Yeah, like that's ugly.
As you can see, we have 3 S endings. Therefore, we have to have 3 branches, 3 blue branches that connect 3 S's on the bottom to a W on top. So, branching at W, partial W, partial X, partial X, partial S, plus partial W, partial Y, partial S. Yes. Plus partial W, partial Z, partial S. There we go. Done.
Wait, why is it partial?
Oh, yes, you're right. Straight through. DZ, DS. Excellent.
You still write the partial part?
For W, you have to, because there is branching. W branches into X, Y, and Z, right? You have to. I mean, as I said, if you just put partial everywhere, I have to accept it because it's correct notation. It's just for your record keeping, you know, when you have to worry about taking partial derivatives and when you don't have to worry about taking a partial derivatives. That's, you know. So, your next exam, which might be next week or whenever you vote, or not have exam, I don't know. But if you are to have an exam too, you must have a problem which will have some simple chain rule calculation that you can, you know, draw. But then you should also have a problem that has something like this, right? Draw the tree diagram, create the formula, and then I give you a whole bunch of stuff in some configuration like this, and then you just plow through it. Without actually doing the work of, it's just developing the formula. Now the hope is that you will be able to use the formula once you develop the formula.
So if we have our exam on next Thursday.
Well, maybe, I don't know. Is it next Thursday?
If we decide, that means the first quiz will be tomorrow.
At 6 a.m.
At 6 a.m. But if we have it on next 2 Mondays from now.
2 Mondays.
Because next Monday we have meetings.
In week 5, you mean?
Yeah.
We don't have time.
Okay. I'm just saying. Then that first.
No, I mean I'm starting chapter 13 next week, whether or not you have exam. That's not.
I think it is. I think it is probably a good idea to start to have the exam on Thursday.
Okay.
You don't want them the same. I think Thursday's a good idea. Can we vote? Yeah.
Do we need to vote?
Yeah.
Okay, so what are the proposed dates?
Thursday.
Thursday and Monday. Oh, it's gonna be fun.
Or no test.
Well, no, you can't do that. You agree as a classroom if there is no test or there is test, and then you go with a Monday or Thursday. Well, let me put Thursday first because it's before Monday. It was week before, right? There we go. All right, good. Which of the 2 days?
Take on test for in-betweeners.
Trust me, you don't want to take.
I'm on Team Thursday.
Team Thursday.
Monday.
Team Monday. Thursday. 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 Oh, we don't need the stream for this, so let me just say bye to these guys. We're working on a test, and then we'll the next lecture will be after these commercial breaks.